Om Swastiastu. Hello everyone, my name is Samuel Benaya Batubara with student number 22055311097. In this video, I will explain about chapter 16 of the book Manufacturing, Engineering and Technology, 6th edition, Sheet Metal Forming Process and Equipment. Sheet metal forming enables the production of light, stiff, and geometrically complex structures such as automotive panels, aircraft skins, cabinetry, and various consumer products. Most shaping is done using press and hard tooling, with stamping being the dominant industrial term for this operation. Shearing is a primary cutting method in sheet metal operations. A punch forces material into a die opening, initiating fracture from both sides. The resulting edge includes rollover, a burnish zone, a fracture surface, and a burr. Clearance significantly affects these features as excessive clearance increases burr height and distortion. Punching force is proportional to the shear area and the ultimate tensile strength of that sheet. Sufficient clearance reduces force requirements but compromises edge integrity. Conversely, very low clearance yields improved edge smoothness but increased force demand and tool wear. Cutting variants include punching, where the slug is scraped, and blanking, where the slug becomes the product. Notching, perforating, lynching, sitting, and nibbling further extend process capability. Scrap ratios can reach 30%, thus optimizing sheet layout in critical or material efficiency. Formability depends on several sheets characteristics: elongation capability, yield point elongation, anisotropy, grain size, surface finish, spring back tendency, and edge condition. Failure often results from localized necking and thinning, making formability in this essential for predicting success in forming operation. The Erickson cupping test evaluates the depth at which a dome-shaped specimen fracture. Forming limit diagrams map permissible strain combination based on major and minor strain axes. Negative minor strain values generally improve deep draw performance and suppress fracture. In bending, the outer sheet fibers elongate while inner fibers compress. The neutral axis shift depending on material hardening characteristic. Minimum bend radius correlates with ductility and sheet thickness. Inadequate radius selection leads to tensile cracking along the outer surface. Rolling direction significantly influences bend performance because anisotropy aligns mechanical properties. Bending transfers to the rolling direction reduces susceptibility to cracking. Non-metallic inclusions serve as crack initiation site and therefore directly degrade bendability. Press brakes are highly versatile machines used for long sheet bend. Tooling flexibility allows rapid changeover, making them suitable for both low volume and custom operations. However, dimensional repeatability depends strongly on operator setup and tool condition. Flanging forms a bent rim and is prone to edge wrinkling if blank holder pressure is insufficient. Having folds material back onto itself to produce aesthetically clean and safe edges. Bedding locally stiffens sheets by thickening the cross-section in selected zones. Deep drawing converts a flat blank into a closed container by forcing it through a die cavity. Blank holder force must be carefully balanced. Too little force causes wrinkling, while excessive force increases friction and tearing. Lubrication and draw bits are typically used for improved material flow. In rubber pad forming, a compliant membrane transmits pressure uniformly over the sheet, enabling smooth surfaces and minimizing die marks. This method is advantageous for limited production runs, where rigid tooling would be uneconomical. Hydroforming shapes sheets or tubes using controlled fluid pressure. it produces seamless, structurally optimized components such as automotive frame and radiator enclosures. Hydroforming offers reduced weld requirements and improves structural stiffness. Spinning forms asymmetric sheets by pressing them against a rotating mandrel. The process is economical for symmetrical components in moderate production quantities and yield smooth surface and continuous fiber flow alignment. Superplastic forming exploits extremely high elongation behavior at elevated temperatures. Verified geometric definition is possible. However, forming rates are comparatively slow, which restrict application mainly to high-value approved press structures. Honeycomb cores provide exceptional stiffness to weight efficiency due to their cellular configuration. When bonded to thin face sheets, they create sandwich panels with superior bending rigidity. Applications include aerospace floor, fairings, and control surfaces. Effective part design minimizes abrupt transitions, sharp radii, and excessive drawdown. Uniform wall thickness must be maintained to avoid localized thinning. Proper bed placement and blank folder force strategies suppress wrinkling and tearing. Mechanical presses offer high production speeds and are preferred for shallow forming. Hydraulic presses provide full tonnage capacity throughout the stroke, suitable for deep drawing. Progressive dies allows multiple forming steps in a single stroke, improving cycle efficiency for mass production. Economic feasibility depends on minimizing tooling wear, optimizing scrap layout, and limiting forming stages. Die cost dominates capital expenditure, justifying high volume production for complex stamping. Automation further reduces cycle variability and enhance throughput. In summary, sheet metal forming delivers lightweight, stiff, and geometrically diverse structures. Process success depends on formability assessment, controlled tooling condition, appropriate lubrication, and carefully balanced blank folder forces. Equipment selection and the operational economic dictate overall sustainability of the manufacturing route. The material of this presentation was fully adapted from Chapter 16 of Kalpakjian and Smith manufacturing process for engineering materials. And that is all of my presentation. Thank you for watching. Om Santi Santi Santi.